Hello everyone, I'm Chris McIntosh. I help teach the statistics courses. I wanted to give you a little supplementary lecture this week on categorical data analysis. This material comes from chapter 10 of the Navarro text. The chi-square goodness of fit test tests whether observed frequency matches expected frequency for a single variable. So it's used to see how closely the frequencies in a categorical variable in the categories of a categorical variable match a predetermined expected proportions. So the assumptions are that you have a single categorical variable, could be nominal or ordinal. Observations are independent of each other, so you shouldn't have like people that are related to each other by some reason, or people in different categories in more than one category. Thus, the next assumption groups are mutually exclusive, and expected frequency in each category should be at least 5. The statistical hypothesis for a chi-square goodness of fit test is H naught, or the null hypothesis is observed frequencies match expected proportions, and H1, or the alternative hypothesis, is observed frequencies differ from expected proportions. And the degrees of freedom for this test is the number of groups minus 1. And we're just getting an overview. This is one of the chi-square tests. There's more than one. And we're not going to be doing a computer assignment on this, but these are the basics of the chi-square goodness of fit test. I don't think Hevie mentioned this particular test in her text. Navarro, in his section about the chi-square goodness of fit test, provides a really nice pattern for reporting statistical results. So he started out by reporting some relevant descriptive statistics to kind of orient the reader to the data. He described the test used and what was being tested, the null hypothesis. He reported relevant statistical information. The chi-square should include the degrees of freedom. N is the number of observations or participants, and then the chi-square value, and P, and whatever the P value equals. And then I always suggest reporting an effect size when possible. And you can calculate an effect size for a chi-square goodness of fit test, but we won't worry about it, but you're going to see it for other tests later on. And then you want to interpret the results for the reader. And it looks like I forgot to delete that from the copied slide, so just ignore that section for the degrees of freedom. The chi-square test of independence tests if two categorical variables are related. There's another name for this test, and it's called the chi-square test of association, and those are used interchangeably. You'll hear me call it one name in one place, one name in another place, and you'll see them printed both ways in different places, so just be used to that. It's used to test how closely observed frequencies match expected frequencies, and there's a formula for calculating that, which your computer will do. You won't have to do that by hand. The assumptions for the chi-square test of independence are there's two categorical variables, observations are independent of each other, groups are mutually exclusive, meaning people can only belong to one group for each variable, not more than one. Expected frequencies in 80% of the categories is at least 5. So if you had 4 categories, then you couldn't, even one category with less than 5, it would be 75% because there's only 4. So you'd have to have like 5 categories and only one of those be less than 5. And there can be no expected counts of 0 in any of the categories. The statistical hypotheses for the chi-square test of independence is the H naught, the null hypothesis, is observed frequencies match expected proportions, and H1, observed frequencies differ from expected proportions. You might also hear me describe it as the null hypothesis, there is no association between the two variables, and the alternative hypothesis, there is an association between the two variables. So you have a little flexibility there in stating those hypotheses. Degrees of freedom are calculated by taking the number of categories in the row minus 1 times the number of categories in the columns minus 1. And if you only have 1 degree of freedom, then you'll use something they call the Yates continuity correction, And you'll see a checkbox for that in Jamovi when we get there. The effect size phi is used for when you have a 2x2 table, or Kramer's V is used when you have a table that's bigger than 2x2, and you're going to see that in Jamovi. Interpretation depends on domain, but the basic guidelines are weak is less than a Kramer's V of less than 0.1. Moderate is Kramer's V of 0.1 to 0.3. Strong is Kramer's V of 0.3 to 0.5. And very strong, anything greater than 0.5. And the format for reporting looks like I have there on this slide: chi-square, and in parentheses, degrees of freedom, comma, n equals the number of participants, equals in the chi-square value, p equals 0.00, give the p-value, that's an example, 0.002, and then Kramer's V, and then whatever the Kramer's V value is, and you'd want to interpret it too. There are some tests you can use instead of the chi-square. If assumptions are violated, if the expected counts are too small, you can use Fisher's exact test. If observations aren't independent from each other, you can use the McNemar's test. And we're not going to actually do those this semester, but just be aware there's some other tests. And you're going to know enough from this class to look up a test like that and get instructions and some basic data if you needed to do something in a situation, or consult a statistician and get some help. I gave you a good explanation of this slide in the computer assignment, so I'm going to forego that right here, but see the computer assignment and look at what I say about the effect sizes and statistical tests. And then see the computer assignment for an example of the null hypothesis significant testing steps for the chi-square test. And we will go through these steps in the computer assignment, so I'm not going to go into depth right here. Okay, that's it. Thank you. Have a good day, and we'll talk to you guys later.